hybrid exoskeletons for muscular rehabilitation. According to the World Health Organization, around 15 million people every year will fall victim to a stroke, and this number is expected to grow by 3.4 million people by 2030. Now, this is especially a problem when you realize that strokes are one of the leading causes of disability in the United States, and they even cause a disability in over half of its victims who are 65 and older. Now, according to this chart by the CDC, strokes are extremely prevalent in the southeastern region of the United States, which might hit pretty close to home for some of us. Now, we might not be able to do enough to stop strokes, but we're certainly not doing enough to treat them. Even after completing conventional physical therapy, only 40 to 50% of patients will receive any benefit. Even when they do, they rarely regain enough motor function to ever walk again. Furthermore, current rehab seems to focus more on the symptoms, not the issue. The highest priority among most stroke victims is to be able to walk again, but many physical therapy experts will seem to focus more on wheelchair mobility more than anything else. Now, part of this might be due to the financial pressure of just quickly treating a patient, as it's much easier to just teach someone how to use a wheelchair than it is to teach them how to walk again. But all of this has just been for one disabling health condition. Parkinson's, paralysis, and many other conditions are out there, and they don't have much effective treatment either. Since traditional physical therapy isn't all that effective, my research is seeking to use exoskeletons to supplement what traditional rehab lacks. An exoskeleton is simply just a wearable robotic device, and it works in tandem with the user. Now, when we add a controlled muscular input to that, it becomes a hybrid exoskeleton. And this is usually done through what's known as functional electrical stimulation, which I'll get in towards the end of the presentation. Now, exoskeletons allow for almost complete and direct muscular control, which makes them much easier to use than many traditional rehab devices. This muscle control might be more difficult, but its effects are definitely worth the added complexity. Sometimes patients will have difficulty performing even a simple muscle contraction, but an exoskeleton can make that motion much easier, making rehab that much more effective. Now, most research in the past has actually gone into lower body rehabilitation just due to the importance of walking, but my research has been focusing more on upper body rehabilitation as it's more a lacking field. So to start taking advantage of exoskeletons, I've used computer-aided design to design and construct an initial test bed that we're kind of using to see the impact an exoskeleton can have in a rehabilitative situation. So this device essentially mimics the motion of an arm. It allows a normal range of motion while recording and assisting the patient. On the underbelly of the device, there's a gear system, which we have a motor and encoder attached to the rotary mechanism. The motor is essentially there to apply an assistive or resistive load, and we'll basically use that to keep a patient's motion in line with the target path. The encoder is then in place to provide position and velocity feedback. We can basically use that just to see how close the patient actually is to what we want them to be. Now, safety is extremely important, especially with rehab. So we've put a lot of software safeties in, basically stopping the software if the motion goes too far or too fast. But even if those do fail, we have some hardware safety implemented, such as this screw here, which acts as a pin, and it basically prevents the arm from rotating past 175 degrees, thus preventing hyperextension. So once we have feedback from the encoder, we can implement what are known as proportional integral derivative, or PID controls. These will essentially take an error function, which compares the arm from where it is to where we want it to be. Then we can integrate it and differentiate it. And then we combine the three into some control logic. And then we use that control logic to determine how much current we actually apply to the motor, and that determines how much correction we end up applying. So now we've actually started collecting data that we can use to start proving the validity of a hybrid exoskeleton in a rehabilitative situation. Essentially, we have a patient follow a given movement pattern with and without robotic help, and then we'll compare the two. So we can basically just track how close someone is to a targeted path. So both these graphs are just for a simple back and forth motion, like was shown in the previous slide. The first graph is with the motor controlling the motion, and the second is with just the human's back and forth motion, no motor involved. As you can see, the robotic path mimics the targeted path much more closely, with an average error of 0.001 radians and a standard deviation of 0.02 radians, while the human path had an average error of negative 0.03 radians and a standard deviation of 0.06 radians, both of which are much larger than what the robot achieved. This essentially starts validating that an exoskeleton is improving human motion. So here's a quick example of one of those cycles. The arm is just moving back and forth. As you can see, there's still some chattering, basically meaning it's jerky a little bit back and forth, but we believe that applying a neural network to our PID controls can actually help compensate for some of that. And now for just a few more things we'd like to implement. These sensors allow us to add more safety and control to our control algorithm, which makes it more complex, but does add some great benefits. First up is an electromyography, or EMG sensor. This device essentially allows us to monitor muscle activity. We basically use one of these to see how much an individual is contributing to the overall motion of the exoskeleton and how much is due to the motor itself. So essentially, the more muscle activity, the more an individual is actually contributing to motion. This is a great metric to see improvement, as if we start to see more muscle activity over time, it means that rehabilitation has actually occurred. We'd also like to implement some force sensors on each side of the forearm, and we can use those to detect if a patient is moving ahead of, behind, or in line with a targeted path. So for a great example, a force here on a bicep contraction, depicted by the large arrow, would essentially mean that the patient's arm is not contracting enough to meet the exoskeleton motion. So the motor is actually doing work to keep the arm in line. A force here on the opposite side would mean the exact opposite. The patient is moving their arm faster than the exoskeleton, so it's actually resisting their motion. Our next biggest step is to include functional electrical stimulation, or FES for short, into our exoskeleton. FES is essentially where we can apply a very specific electrical current to a targeted muscle group, and we can elicit a muscle contraction out of that. It essentially involves connecting electrodes to the patient's body, which are then plugged into a simulator, which is then controlled by a computer. Now, FES is extremely helpful in patients who have difficulty contracting their muscles, such as those who have had a stroke, as FES can safely cause muscle contractions while their nervous system might not be able to. Because of this, we can apply FES to significantly improve recovery and overall muscular strength, as the muscles themselves are actually doing more of the work. Now, one interesting facet of FES from the controller side is that it essentially allows us to treat the patient like a robot, which allows for a greater degree of robotic control of the exoskeleton as a whole. In the case of FES on the legs, like in this image, the computer can essentially view each of the patient's legs as a controllable output, which makes almost all of the exoskeleton completely computer controlled, giving us almost complete independence from a nervous system. Now, we of course intend to implement this with the arm, but we want to take it to a new level by using FES on both the bicep and the tricep, which would result in total muscle usage. Now, the exoskeleton is already pretty complex and has some chattering in it, but FES will make that even more complex. Because of this, we intend to implement what's known as an adaptive neural network, and this will just essentially help us do some of the fine-tuning so that it's much easier to control. And so once we're able to successfully bind FES with the test bed I've constructed, I really believe we can start to really make a difference in disabled individuals' lives and just give them a much better quality of life. And with that, I'd like to thank my faculty mentor, Dr. Cousin, for helping with this entire process, and just open the floor to any questions.
So you were talking about using neural networks to improve your system. Could you talk about that more?
Yeah, so basically, as you can see here with the motion, it's kind of jittery or has some chattering in it. It goes back and forth. Some of this might be due to friction, but a decent bit of it is also due to the controls. So basically what will happen is it'll try to reach a targeted state, it'll reach the targeted state and stop, but then it has to reach the next targeted state, so it picks back up again, which results in that kind of jerky motion. But once we add even more sensors in FES, it'll become even more complex. So a neural network will essentially just do like a quick little trial run, and it'll basically be able to help us figure out some of our constants that we're multiplying everything by and help smooth things out a lot.
How would a person who moved their arm, such as in your human position graph, know the path they needed to follow?
So as you can see in this graph here, we have a targeted and an actual motion. So what would actually happen is there would be a computer screen next to the patient that they would be able to watch, and then the target path would actually be live broadcast on the screen, just tracing it out. And then we'd overlay the actual path where the arm actually is with that. And so essentially the patient would be told, try to make the two overlap as much as possible, and then that would just allow them to kind of see what they're doing.
You mentioned that the motor could be assistive or resistive. Is there any way to intentionally make it resist by motion by a certain amount so that the patient has more of a challenge?
So we can't just tell the motor to just straight up resist, as unfortunately that would kind of mess up the control logic. But what we can actually do is we can change the path some. So currently it's a really slow, methodical back and forth motion, which is relatively easy. But if we were to change the path, say make it a little faster or make it non-uniform, we would be able to just kind of have the patient have a little bit more of a challenging path and thus have more rehabilitation.